First of all, a special welcome to Mehul Shah. Mehul Shah is the founder and CEO of Clean Core Thorium Energy, a Chicago-based firm, who's been instrumental in putting together this idea, this panel, and got everybody to work on this one. Welcome, Mehul Bhai.
Thank you very much.
The key participants, let me start with Elena Teplinsky. She's a graduate from Fordham University and Georgetown University School of Law. Elena is a leading member of Pillsbury's International Nuclear Projects team and Energy Industry Group deputy leader. As a young student, she showed remarkable perception in understanding issues relating to immigration, race, and social psychology. She focuses on international nuclear energy matters, including advice to US and global clients on transactional and regulatory issues. While she obviously has an impressive resume, I'd like to highlight a few that are immediately relevant to the struggles faced by the world as it races towards becoming more sustainable. A published insights European Union's in-house science body that determines that nuclear energy is a sustainable technology under the EU's green finance rules. The ruling has positive impact for government and private sector support for nuclear technologies in the EU and beyond. You know, by the way, how this whole conversation started was about 3 or 4 weeks back when we were talking. Dr. Kakotkar said, you know, we used to talk about climate change. It became a climate emergency. Now we are talking about a climate crisis. So we've got to get started. Welcome, Elena. Glad to have you here with us this evening. And the next is Mr. Seth Gray. He's the president and CEO of Lightbridge Corporation. Lightbridge Corporation is a publicly traded company headquartered in Reston, Virginia. An interesting component of his work is advancing state-of-the-art nuclear fuel technology. This technology has the potential to transform not just the efficiency and safety, but the economics of nuclear power plants. This is an interesting anecdote about him. While in law school, Seth Gray decided he was going to pro bono represent an actual dissident in the Soviet Union as part of a final class paper. Through help from people at the State Department and NGOs, Gray identified a man who designed the guidance systems for Soviet cruise missiles and nuclear submarines. With the support of a major law firm, he went to Russia and filed a brief on his behalf with other American lawyers. That was the first time Gray met American and Russian nuclear engineers, learnt about that field. Since then, he's been working in that field. He speaks on economic aspects of using old nuclear power plants and coming SMRs, the small modular reactors, with newer fuels and their efficiency and safety aspects, as well as the new project dynamics and economics from aspects like nuclear waste disposal and so on. Gray holds a number of interesting posts, including member of the Civil Nuclear Trade Advisory Committee to the US Secretary of State, a group on climate, nuclear, and security affairs at the Council on Strategic Risk, and is also a member of the Board of Directors of the Virginia Nuclear Energy Consortium. Welcome, Seth Gray. Then we have Dr. Sean Mcdovit, an accomplished nuclear engineer, professor of nuclear engineering at the Texas A&M University, and director of the Nuclear Engineering and Science Center. One of his very early and extremely distinct accomplishments is that while in Purdue University as an untenured associate professor of nuclear engineering, he began establishing the Fuel Cycle and Materials Laboratory, FCML, which he subsequently moved to Texas A&M, which has grown in size and stature. His multidisciplinary experience in nuclear materials and chemical engineering has equipped him with the flexibility to make research contributions in a diverse range of subjects. He earned his PhD from Purdue University School of Nuclear Engineering, where his research focused on uranium and zirconium alloy nuclear fuel for the integral fast reactor. Dr. Mcdovit continues to manage the much upgraded FCML in Texas A&M. The primary mission of the FCML is to study current issues in the nuclear fuel cycle, including materials and chemical processing, advanced fuels and nuclear materials. And in 2019, the NSC was renamed to the Nuclear Engineering and Science Center and now comprises a couple of reactors there and nuclear science research laboratories and the Nuclear Power Institute for Workforce Development. Welcome, Dr. Mcdovit, a very accomplished professor indeed. And finally, the chairperson for this evening, Dr. Anil Kakotkar. This introduction is something that I always enjoy making. When the President George W. Bush visited India in 2006, Dr. Kakotkar was introduced to him. President Bush asked him, "So, you are that Kakotkar. Are you happy?" Just imagine the amount of trouble Anil Kakotkar has given during the civil nuclear discussions of the deal signing. Finally, the President of the United States, none other than him, wanted to make sure that Kakotkar was happy. Welcome, Dr. Kakotkar. I don't need to read your biodata. No. All of them know you. Thank you very much. And the only point that I wanted to make is that you're consumed by your current passion to get to the third stage of the three-stage nuclear energy journey outlined by Dr. Homi Bhabha several years back. Thorium-based nuclear energy that is proliferation resistant and less hazardous nuclear waste is a key part of Dr. Kakotkar's work. Thank you once again for joining us this evening and morning for all of you. Over to you, Dr. Kakotkar.
Well, thank you, Mr. Lakshmanarana, and thanks to everybody who is in this conference, and my special gratitude to our colleagues on the panel. Together, I think, let us attempt to create a perspective to address the theme that we have for this conversation today. Is nuclear energy a solution for sustainable development? Mr. Shah, can you share my slide from there?
Yes, sir.
Yeah, please. So I have just, I think, 5 or 6 slides, and I had deliberately chosen this one as an introductory slide. This actually is a picture of Kaiga atomic power station, and you can see 4 220 megawatt HWRs operating there. It is, well, they started at different points of time, but roughly around decade of continuous operation has been there. Their units are working extremely well at plus 90% capacity factor. And in fact, in 2016, Unit 1 made a world record of uninterrupted run of 962 days. So, well, the point that I want to convey with this title slide is that we are talking about answering this question before us. For the emerging economy countries, leveraging PHWRs, which are a very successful technology. Now, Indian Power Program, of course, it has moved on. While there are 11 more such 220 megawatt units in operation in India, there are other 2 540 megawatt PHWR units operating at Tarapur. And also there are as many as 16 700 megawatt units under construction, the first one of which has been connected to the grid and is undergoing trials right now. So there is a fleet mode of construction of these PHWRs underway. In India, we are going to also add the power program by additional reactors in the form of fast breeder reactors, and also reactors constructed through cooperation with other countries. And VVR reactors, in fact, 2 are operating at Kudankulam and 4 more are under construction there. What we are discussing today is a somewhat a bigger problem. We are not talking about India specifically. We are talking about a global problem and how to address the issue of such. Can I go to the next slide?
Yes, sir.
So how to address this issue of sustainability in the context of climate crisis, which is already here. And if you want to address that issue, of course, there are countries which are very advanced and they're already operating nuclear power program. But most of them, there are exceptions, but most of them are the so-called advanced countries, or many of them are actually OECD countries. The map of the world in the top right-hand corner, if you see, there are four shades of blue, and then the rest of the world is all gray. Those blue shaded countries are really countries with high human development index, between 0.8, 0.85, 0.9, 0.95. So these are the countries where per capita electricity consumption also is very high. Now, of course, you want to reduce the carbon dioxide in the atmosphere or the global warming. There is a question of decarbonizing that, and so there is a question of adding more nuclear, more renewable in place of existing electricity plants or other energy plants which are based on fossil fuel. But if you look at the bar chart at the bottom right hand of this figure, you would notice that OECD countries, which actually represented by the dark blue band, this growing, total energy is growing, but it is very slow, more or less stable. So while there is this challenge of decarbonizing, but if you see the rest of the world, the non-OECD bloc as it were, there you would see the demands are higher, and there is a much higher growth going forward up to the middle of this century. And so there is the dual challenge of decarbonizing existing energy systems, but also adding more kind of clean sources of energy. And world is doing quite well in terms of adding solar and wind, and of course a few other renewable energy options. But most of them, or majority of them, the big chunk of that is actually variable energy sources, variable energy generating sources. And you can't run grids like that. You must have a stabilizing factor, and mostly derived from baseload generating source. Otherwise, of course, you have to worry about the storage and other electronic modes of control, which adds to quite a bit of cost. So the point is, the challenge is in the emerging economy countries. And there, if you want to do, then we must have clean energy systems. And on that, we must have baseload generating system, which actually means nuclear, which are fit, which meet the requirements of those countries. If you want to really address this question that is before us. Can we go to the next slide?
Yes, please.
Next one, please. Yeah. Now, this is what I want to focus really. This actually, the information is from an MIT study, The Future of Nuclear Energy in a Carbon Constrained World, which was published in 2018.
What is this?
Now,
Oh,
on
just
the
take it
left
inside
hand
and bring my just going
side,
to the food.
there is data
Yeah, just bring
about
my protein
the
shake.
average generation
not in a glass.
costs in a region in United States and also in a region in China. And you would notice that if you, when if you talk about the current levels of the emissions, carbon dioxide emissions, then whether your mix has nuclear or no nuclear, it doesn't make much difference. But if you start moving towards low carbon or zero carbon, for that matter, if you see in the that New England chart, the extreme right-hand side block, the orange bar there is the situation when there is no electricity. No, I think we can remain on the previous slide. And you would notice that without nuclear, the tariff to the users, and this is average tariff, including system costs, it can become 2 times, or in Chinese case, it can become even 4 times. And this is something which is not appreciated because people are looking at the current situation or a marginal change, and you don't see that factor. But if we don't correct and bring in nuclear right now, going forward, we may have to invest too large amounts of money. And this is what has happened in Germany for that matter. But that's a separate story. And for the optimum tariff, the level of electricity coming from nuclear, it could be as high as 60% or 80%. So, and I think we need such studies. In India, I have not seen a single study of this kind. And unless we have such reliable studies, it may be quite tough for us. Can we go to the next slide? Next one, please. So it is in this context that I personally very strongly feel that we must bring in nuclear and overcome the challenges that are there for nuclear. Nuclear has challenges. Proliferation is a challenge, safety is a challenge, waste management is a challenge. Many countries, small countries, suddenly taking on a large reactor, they see a fair bit of financial risk. That is a challenge. And there are lots of new designs, because requirements at different parts of the world are different. But the question is, for a emerging economy country, they would want a proven system which has been already running well in host country or some other countries. And they won't want to be the guinea pigs. Now, I think the best fit for all this, in my mind, is a 200 megawatt pressurized heavy water reactor fueled by thorium and, of course, enriched by high assay, low enriched uranium. Now, PHWR are proven reactors, a lot of experience around the world. These are the smallest commercially operating units, but they compete with even large units despite the challenge of economy of scale, simply because they are made in India and we make things much cheaper, particularly high-tech things in India. And well, it's happened in space, it happened in atomic energy, it happened in many other tech sectors. And of course, thorium gives a lot of properties which enhance safety, which enhance performance. And of course, there is PHWR has a lot of cold moderator in the reactor core. That also contributes to safety. The fuel burn up because of thorium goes up, so the spent fuel becomes just 1/8. And the capital cost of these reactors, as I said, is low, but operating cost also there is benefit. And so I have been arguing for some years now that heavy water reactors fueled with thorium HALEU combination are really the best choice. Next slide, please. Next slide. Yeah. Now, this on the right-hand side, there is some data to say that, in fact, thorium shows some benefit in all thermal reactors, but the benefit is best in PHWRs. And particularly if you see the bottom right-hand corner figure, the red bars, which actually talks about the plutonium generated. And you would notice that the plutonium generated, it becomes negligibly small with thorium fuel because there is deep burning of plutonium to produce more energy, and whatever is left is very heavy on even isotopes, so it is a completely proliferation resistant. Now, Mr. Mehul Shah, who is there in the audience, in fact, he has been a thorium enthusiast for more than a decade, or maybe more than that now. And he picked up this thought, and his company, CCTE, has developed this anil fuel, advanced nuclear energy for enriched life, that can work with heavy water reactors, both PHWRs as well as CANDU, with little change to the reactor itself. And so his company is collaborating with Texas A&M University, and Professor Mcdovit is here with us to tell us, in fuel manufacture development with the Idaho National Laboratory for the irradiation and post-irradiation examination. And they are also working with a few more universities, particularly MIT, on fuel modeling. The ATR, which is at Idaho National Lab, is a reactor with very strong powers. It can do whatever we can do in India in just 1/10 the time. And so it can deliver fuel qualification through irradiation much, much faster. And that's strength. And of course, we're talking about the high assay, low enriched uranium. And the United States is rightly praised for being the fuel supplier for that. So I think it's a win-win situation if you address the challenges of third or the emerging economic countries to provide the clean baseload energy solutions through this anil-fueled 220 megawatt heavy water reactor, or even other heavy water reactors. And that is what we are going to talk more about it in a conversational mode. Before I move to my next panelist, I would request Mr. Mehul Shah to tell us exactly what is happening in just 2 minutes about this development, and then we will move on to Ms. Elena Limpis. Mehul?
Most certainly, Dr. Kakodkar, thank you. And first of all, I thank CIC for this opportunity, and I thank the panelists for being part of this discussion. And most importantly, we are grateful to Dr. Kakodkar for his mentorship, and we are committed to be part of his vision and the mission in fight against climate crisis. Let me share some current state of play at CCTE, as we are thrilled with the progress with our innovation. Anil fuel is designed to deliver cost-effective, clean baseload energy in very short term. At the same time, it will address the key barriers of nuclear, like proliferation, waste management, and safety. And like Dr. Kakodkar explained, currently our fuel is being manufactured at Texas A&M, followed by first of its kind irradiation testing and qualification at Idaho National Lab. In collaboration with MIT and INL, CCT is developing extension to the US Department of Energy's Bison code, which will eventually validate anil fuel and the future fuel of thorium-based advanced fuel. Patent for anil fuel is filed with US Patent and Trademark offices as we speak, and we are establishing a supply chain for the commercial production of anil fuel. We are in conversations with fuel fabricators in US and Canada. We have signed MOU with US-based Centrus Energy for the supply of HALEU, and exploring several sources, including India, for the supply of thorium for anil fuel. And in short term, CCTE plans to deploy anil fuel in existing refurbished CANDU reactors. And in longer term, we plan to deploy anil-fueled Indian or Canadian heavy water reactors for emerging and established countries for clean, safe baseload energy. So we are very excited that industry is now recognizing the benefits of anil fuel. Now CCT is building partnerships with like-minded investors and the stakeholders. We are in dialogues with Reactor supply out of India and Canada, utilities in Canada and Romania for refurbished reactors, and dialogues with emerging countries for new reactors. And I really appreciate and thank you for hearing our state of play. And if you have any questions, please feel free to reach us at cleancore.energy. Thank you. Back to Dr.
Thank you, Mr. Shah. And may I now invite Ms. Elena Teplinsky to make her remarks.
Thank you so much, Dr. Kakodkar, for moderating this discussion. It's an honor to be in the same panel with you. Thank you very much for to Mr. Shah for inviting me, and as well as to CCI for hosting this discussion. I have had the pleasure to advise governments, vendors, owner-operators in the nuclear industry for more than 15 years, and I'm a part of a group at Pillsbury that's been doing this for more than 60 years. So as part of our experience, we've really seen the evolution of the nuclear industry, and we've also seen, some of the challenges that the industry has faced. I'm going to share a slide just so that you can get a bit of a visual of, how we see the world today when it comes to the potential expansion of nuclear power. I could share many slides with you that demonstrate that we unfortunately are not on the trajectory to meet climate change mitigation goals. Unfortunately, despite the very large scale rollout of renewables over the past decade, and in fact, the renewables have become much cheaper, we are still burning as much fossil fuel as we were about 15 years ago. And increasingly in the past 15 years, there has been a focus on whether nuclear technology can present a solution to the climate challenge. If you look at about 15 years ago, this map was probably not as big as far as countries considering nuclear, but it was big enough. There were quite a few countries looking at nuclear because it presented a baseload, reliable source, and the technology was well proven. A lot of countries had experience building nuclear, so there was what we called at the time the nuclear renaissance, where a lot of countries started considering and building new nuclear power plants. While some countries were successful in doing so, you look at China, for example, that is on its way to potentially overtake the United States in the next decade or so as the number one nuclear reactor operator, because they're building reactors so fast. India has had a great trajectory in building large reactors. We've seen newcomer countries, for example, like the UAE, construct these large reactors on time and on budget. But the thing is that, very few countries have the capacity, both with their governments and their private industry, to undertake these very large and complex projects. We're talking about gigawatt scale projects where the financing is mostly available from government sources. So that means that smaller countries, as well as private players, simply just do not have the capital outlays or the financing available to undertake these projects. You also have, a lot of countries that have smaller grids that are looking to nuclear energy for other purposes, such as desalination. And increasingly, there was a very important discussion that started in the past year or two about the use of nuclear energy to produce hydrogen. Which is a way to not only resolve some of the issues with energy storage, for example, from renewables in the electricity sector, but it's also a way to decarbonize some of the very difficult sectors, industrial sectors, such as transportation, including marine shipping, iron ore production, cement production, and others. So increasingly, nuclear technologies are being sought as a decarbonization solution, beyond just electricity and beyond the typical markets. And what you can look at this map, what is in green, these are countries that have existing nuclear power plants, and they're also considering small modular reactors. And why is that? For some of these countries, even if they actually have, the funding to deploy large reactors, they are looking at small reactors for lots of different solutions, and also for being able to locate and site nuclear reactors closer to population centers, use them for non-electricity uses, as well as involve some of the private players. If you look at the countries that are in yellow, these are generally newcomer countries. And with the exception of a country like Australia, most of these countries, simply do not have the financing available to construct large reactors. Many of them are looking at small reactors, but financing can even be a challenge for these. And these are countries that are generally fast growing. They have a demand for electricity. They have a demand for heat. They are looking at nuclear as a technology that can provide a sustainable solution. So small reactors, small modular reactors can be a solution for these countries because it meets the grid requirements. They also are less capital intensive, and they can be an interesting option. So that's the map today. I will leave it at that. There's much more discussion to be had about the opportunities and challenges, and I'll be happy to make comments further on.
Well, thank you. That was very interesting and very useful. Maybe we can start getting into a conversation right now, and of course we'll come back again for a group conversation and then a discussion with the audience. But if I can request you to little bit reflect on the, we're talking about this emerging economic countries or countries in yellow in your map, except of course Australia. Now, would you like to talk a little bit about the sort of security, political, legal dimension of nuclear power establishment in those countries, and in that context, what do you think of the proliferation resistance feature? What role it could play, if you have any views on that?
Absolutely. Nuclear security is a big consideration, especially as you're looking at regions that don't necessarily have, the type of security that one would expect for a new nuclear power plant. And sometimes it takes people by surprise to see some of these countries that do have major security issues considering nuclear, but they are considering nuclear because there are very few other choices they have, to provide a sustainable development solution. These countries, it's worthy of noting that many of these countries do have research reactors, nuclear research reactors, so they have some experience, but of course, the security issues associated with a research reactor are not as significant as those associated with a larger nuclear power plant, even if it is an SMR. And most certainly the non-proliferation community needs to be on board in order to support the development and the deployment of these reactors in these new countries. So non-proliferation is going to be a key question. And any country newcomer country that decides to pursue nuclear for the first time beyond a research reactor is going to have to demonstrate to the international community, to the IAEA, to vendors as well, that it can meet these nuclear security challenges, in part by choosing technologies that offer really good non-proliferation resistance.
Thank you. And I would like to raise this one more sort of point in similar vein. Traditionally, the light water reactors are fueled by low enriched uranium. Now, of late, there is this discussion on the high assay LEU being a significant driver of the fuel for nuclear energy generation. And I think I noticed there is some policy evolution taking place in United States with respect to the HALEU supply chain. And of course, companies are gearing themselves. So it will be interesting to hear from you, your perspective, a legal who understands the nuclear politics, as to this transition, of course, it's not going to replace, but this kind of new emergence of HALEU as a fuel for power generation. Would you like to comment?
Absolutely. So, in the United States, you have about 50 to 60 companies that are developing new reactor designs, whether there are existing light water reactor designs, that are now smaller, more modular, or advanced reactor designs. And I would say the majority of them are actually advanced reactor designs. And most of these designs are relying on HALEU. And there's an increasing understanding, the U.S. government has invested, provided research and development funds to many of these companies, licensing support to many of these companies. They're looking to these companies to be exporters to the international market, as well as drivers of nuclear growth in the United States. But there's currently no, HALEU domestic supply outside of what the national labs can potentially provide. And HALEU currently is only available from China and from Russia, which of course are competitors of the United States. So the U.S. government has understood this message. The industry has made it, very loud and clear. We need domestic HALEU supply. And for that reason, the U.S. government has provided significant funding to companies such as Centrus Energy to develop these homegrown HALEU production capabilities. And, there are also some legal and regulatory issues around HALEU. For example, transportation, you need special types of casks. There are existing regulations that more or less address it, but the regulations are sort of being streamlined. The NRC is providing additional guidance. There's understanding that, even though the fuel comes after the reactors are, close to, finishing construction, we can't wait. we can't wait to construct, 70% construct the reactor and realize we have no fuel to fuel it. So because of that, HALEU production is one of the number one priorities for several nuclear energy bills that have been passed to Congress, and it has huge support from the U.S. government.
Thank you, Ms. Elena. We'll come back to other discussion also later on in our general conversation. So if I can now move to Professor Mcdovit and invite him to make his remarks. Professor Mcdovit.
Well, good evening. From where I'm sitting, it's good morning, but I'd like to start by thanking CIC for inviting me to be here, and to Dr. Kakodar to moderate this panel discussion. And just start with a few remarks. I visited India in 2007. I went to IIT in Kanpur, and I visited the Chennai, the Indira Gandhi Center in Chennai. And at that time, I had been completing work on a thorium-based fuel concept while I started while I worked at Argonne National Laboratory. And so in a sense, I've been working with thorium-based fuels for more than 20 years. And I've been a nuclear engineer and working with nuclear fuels for more than 30 years. And one of the things I often tell my students is every fuel selection has a context. And that's something to back up and look at the idea of nuclear sustainability as a whole. I've worked on metallic fuel for fast reactors, molten salt fuel for the new or old molten salt reactor concepts, and silicide nitride fuels for accident tolerant fuel concepts. And so there's different reasons why you would pick a fuel, and it has to do with the objectives you're after. With the particular topic that's one of the things we're talking about mostly today, which is this anneal fuel, which is a HALEU uranium-based and also heavily thorium-based fuel that fits into the PHWR. That's the context, and it provides some interesting game changers with respect to how that fuel could be applied around the world. And a couple of other concepts on sustainability, which is one of the other words in the title of this conversation. Back as a young engineer, I entered nuclear engineering with enthusiasm, but a lot of it had more to do with youthful optimism and just the cool factor of what the science was that I was looking at. Very quickly, it doesn't take long when you get into nuclear engineering training to understand that the physics and the basics lean toward a scientific version of sustainability that you can see very clearly. But there's a social, political aspect that you don't know in school when you come to implementation of these technologies. And so a lot of times when you get into things that on paper, you very quickly go to waste management and nuclear security and all these things that you can say, these are the benefits, but the implementation and the application of these benefits take a social will that is part of the challenge that is beyond the scientist and the engineer, but it takes a group like you have assembled here to see the context and the perspective. And so as we look to a sustainable nuclear future, it's got to be a piece of the puzzle with solar, with wind, with anything else. It's not the only thing, but it is a emissions-free nuclear technology. So it has a lot of benefits like you already highlighted. So let me go ahead and take my 5 minutes and focus on where we're at. It's been mentioned already, but what we're doing with this anneal fuel concept. Because I could talk an awful lot about all the other fuels I work with even now, but I think it's best to stay focused and take a look at this concepts. This idea that this CCTE has created, I got involved with. It's almost 2 years ago now. It's close to 1 to 2 years ago, working with Idaho National Laboratory, and some colleagues of mine were talking with CCTE about doing an irradiation test, and they involved my laboratory, which was mentioned earlier, the Fuel Cycle Materials Laboratory. We have a hands-on laboratory. You can even see some of our researchers making the anneal pellets. The concept that we're after is that there's going to be an irradiation test that begins later this year, according to the current schedule. And the concept of the anneal fuel is to have this thorium uranium oxide mix that has high enriched uranium that will allow it to burn for a longer period, and then the thorium mix and this central annular hole. And so in our lab, we've taken the concept sketch on the left and moved to making pellets on the right. And you can see that we've been successful in starting this, and we're starting to already prepare them. And under the Idaho National Laboratory QA program, we're going to be sending those to Idaho in the May timeframe of this year. And this picture on the lower left comes from Idaho as they're preparing this experiment to go into the advanced test reactor. We're looking to build 12 rodlets of these pellets of various compositions and various geometries to go in and then be pulled out at different burnup levels with a maximum of pretty high burnup of 70 gigawatt days per ton. And just to highlight that that's the nature of the project that we're working on. And there's a lot more I could say, but I also think it might be best to wait for questions and see what direction you'd like this to go in, because nuclear fuel, while it's a niche technology area, it has so many variations that you can make a concept design change. Like instead of doing something like this PHWR implementation, you would be doing something like a high temperature reactor for hydrogen production. That's two different things, two different fuels. But in this particular case, one point I would like to make that I forgot to say, the various reactor design programs that are being spun up or resurrected to address certain design application problems, if you're starting from the perspective of designing a new reactor, you are looking at a very long lead time. People say 20 to 30, maybe 40 years to get a reactor designed, qualified, regulated, and built. Whereas this particular anneal concept, the PHWR is already a design in existence. It's being marketed around the world, and this fuel is being designed to fit right into it, to where, assuming things are successful, it would be able to be implemented less than a decade, and I believe the aggressive time frame is less than 5 years from now. So it's a near-term solution that is actually in hand. or on the way to be coming in hand. So those are my opening remarks, and I'll pause and we can talk about this more as we go.
Thank you, Professor Mcdovit. And no, I think you are absolutely right. One has to look at the fuel and the reactor as a combination for everything in terms of reactor performance, even in terms of the safety behavior and so on and so forth. And we all know that the materials do play a very important role. For example, the steam cycle efficiency is directly dependent on the temperature, the structural materials, the fuel cladding, how high we can go. Same thing about the fuel, for example, between the melting point and the operating point, how much margin you hold, and so on. These are some very broad, simple things, but there are more details to worry about. And I personally believe that what is being attempted through annealed fuel in PHWR is to in fact improve that combination, fuel reactor combination, from natural uranium heavy water reactor to this. It cuts down the total fuel consumption. It allows somewhat greater safety margin, for example, because thorium thermophysical properties are better in terms of conductivity and all, but in terms of melting point is much higher. So you do end up getting higher margins. And we don't have time to go through these details, but there is that, and there are many other, and I'm sure Mr. Seth Gray is going to talk about the Lightbridge fuel, which also essentially attempts to do similar thing in context of PWRs. So, but would you have any additional philosophical thoughts, as it were, in terms of this fuel reactor combination and the role materials play in that?
Well, eventually you have to move from a paper design to build something, and then beyond that it actually has to function. And so the materials are a key element of that. And I've spent my career trying to bridge the gap between a nuclear engineer and a material scientist and and the nuclear waste discussions. I've worked in that as well. Having somebody who can speak all of the trade languages across the different disciplines and try to be a connective fiber is a little rare, because a reactor designer will say, well, we'll design this reactor. It works perfect on paper, and the material scientists can figure out how to make it work, or the chemical engineers can figure out how to make it work. But it needs to be a cross-disciplined activity, but it's not all science. It's also regulatory. And then it's also, like I said, social political. And you can have the best solution that can never be built, or you can have something that can function. It's very similar to some of the technology competitions we've seen through my life, Mac PC, or some of the video technologies you've seen. The most elegant technology doesn't always win the market. And so it's really more a matter of what functions, what works, what's cheap, what's economical, what has the best benefits, and what do you invest in and actually commit to. Because one of the biggest problems we have is an attention deficit disorder to these design concepts, where something becomes new and improved for about 5 to 10 years, and then we abandon it for the next new and improved. And so it takes a commitment to excellence and a commitment to delivery that's as much part of this problem as the tech science and technology.
Thank you. And I would like to ask one more question, if you permit. And that is the challenges with thorium in terms of fuel fabrication. The thorium is known to be a very stable material, chemically inert material, and a lot of advantages get derived out of those properties.
Yes.
But the same thing becomes a challenge when it comes to fabrication. And would you like to comment something on that?
It certainly is unique when you get to thorium, and to be a little scientific for the crowd at the moment, it is in the chemical valence structure, it only has one valence state of interest, to where it doesn't have the ability to move its electronic configuration up and down the stability ladder. As you say, like uranium and plutonium both have multiple valence states of existence. That gives you processing options for chemical separations, for sintering, for the various behavior at different temperatures. You're stuck with THO2 and just THO2. There's not a lot of stoichiometry variations. That challenges your processing to where when you get good at it, you've got a product that is also very stable for disposal. So it's one of those things where it has its cons in processing and its benefits in waste management. And in accident scenarios, you have a water incursion to thorium. You're going to have a slower reaction rates and things like that in an accident scenario. Not that we want to talk about accidents ever, but you need to consider those things when you're designing fuel. So when you get to this concept of a mixed thorium-uranium, you actually gain some benefits of the uranium back into processing. So in a sense, all it really means is in the processing, you've got to do different pressures for the powders, different temperatures for the sintering to get it to a nice high density. And once you've got that final product, you've got the benefits of thorium there. And one of the properties that hasn't been mentioned but is very important for thorium, that's also sought in these other things, is its thermal conductivity. Minimizes things like fuel swelling, fuel migration, fuel restructuring during operation. It makes it a much stronger, viable fuel as far as fuel performance issues goes. So that's maybe a little bit of a rambling answer to your question, but those are my first thoughts to what you said.
Well, excellent. Thank you so much, Professor Mcdovit. And shall we now move on to the next panelist, Mr. Seth Gray, Chief Executive Officer of Lightbridge. So, Mr. Gray, may I invite you to make your presentation?
Well, thank you, Dr. Kakatkar, and it's an honor to be with you today and to have been invited by CIC to participate. Lightbridge is designing a new fuel for water-cooled reactors. Our principal focus is on light water reactors, particularly pressurized water reactors, although the fuel variants could also be applicable to pressurized heavy water reactors. When we were starting out, we also started a business we thought should exist in the world, which was advising countries that never had nuclear power reactors how to obtain them and do so very responsibly. And we ended up writing the strategic plan for nuclear power for the United Arab Emirates and have worked in many other countries doing that. And then launched our nuclear fuel development effort that's led us to work with many excellent people, including Sean Mcdovit and Elena Teplinsky, and who've helped us very much in this development. Presently, we have two funding mechanisms from the U.S. Department of Energy called GAIN vouchers, one to work at Idaho National Laboratory and one to work at Pacific Northwest National Laboratory in the United States. And while we began the project with a focus on design for large pressurized water reactors, we've been shifting recently to also have a focus on the small modular reactors, the SMRs. And in particular, what we're designing is a metallic fuel, a uranium zirconium metallic fuel, very different fuel than what has been used in these reactors previously, not pellets, not tubes, an extruded metallic rod that we developed. We've also developed the manufacturing method. And with the small modular reactors, there are 4 points in particular that are leading us to bring them into focus now. One is that this new fuel could give a pressurized water reactor a 30% power increase. And for a newly designed small modular reactor, that is quite feasible to design and deploy the reactor around the fuel to benefit from the 30% power uprate, which lowers the levelized cost of electricity, the cost per unit of electricity sold. And one of the main points of these SMRs is to have a lower cost of electricity to compete with other methods of generating power. A second reason is ramp rate. the ability of the fuel to go from zero power to full power very quickly and back down, or move up and down to load follow with renewables on the grid as the sun shines, as the wind blows. And we think that small modular reactors with our fuel can operate on the grid with renewables very well. A third is safety issues and pressure drop issues that we think are very significant with this fuel to translate into economic savings, including what could be an emergency planning zone only to the site boundary of the plant, reducing emergency response costs, not needing nuclear grade backup diesel generators, and other safety measures that translate into economic measures. And the fourth is the non-proliferation, the increased proliferation resistance. The large pressurized water reactors are very expensive. And that's one reason they've been limited in number and to a small number of countries, making them much easier to safeguard those plants. As we move to much less expensive small modular reactors that can be produced in factories or shipyards and then shipped to sites, we could have thousands of them in over 100 countries. And the non-proliferation aspects become even more important. And we think the non-proliferation aspects of what Lightbridge is doing will be very important to SMRs. Another reason is that our focus at the company, a focus in today's event on this panel also, is nuclear technology to help prevent catastrophic climate change. And there simply won't be enough new large PWRs built to make that much of a difference globally for climate change before 2050. We have 29 years to meet the IPCC goals of staying below 2 degrees of warming. And by Lightbridge's calculations, the number of large reactors of equivalent new clean energy the world will need between now and 2050 is more than 20,000 large reactors of clean energy equivalent. Now, not all of that will be provided by nuclear power. Some will be renewable, some will be other sources. But if a quarter of it is nuclear, that's over 5,000 large reactors equivalent. Nobody, not even China, Russia, is talking about even a very small fraction of that number of large reactors being built, maybe a couple hundred. So to meet climate goals with nuclear, we need very large numbers, thousands and thousands of smaller reactors. And that's where Lightbridge's focus is going more. Dr. Kakodkar had mentioned the promise of next generation reactors, and the other speakers have mentioned them, and we at Lightbridge certainly support their development as well. However, in a world where designing, licensing, deploying a whole new kind of reactor takes so long, and needing thousands of reactors to matter for climate goals, I think it's much more likely that we will meet climate goals with current reactor technology, improved a bit in the current reactor technology for light water reactors, for pressurized heavy water reactors, and also with advanced fuels, like what Lightbridge is doing, what Mehul Shah's company is doing for new fuels for existing types of reactors, are much more likely to have thousands of new reactors deployed in 29 years than whole new kinds of reactors, although we'd like to see them start to develop and move ahead faster as well. And I'll end with one more point relating to clean core thorium energy and what our friend Mehul Shah is leading there on combining thorium from India with HALEU from the United States in an Indian smaller reactor design, a 220 megawatt PHWR, which is that many of us were involved in various ways on the US and India nuclear deals, leading to membership in the Nuclear Suppliers Group, leading to the 123 agreement for civil nuclear cooperation between the US and India. And I think that's been an underutilized benefit and agreement. I wish we could have seen more cooperation coming from an agreement that officially is called an agreement for civil nuclear cooperation. And I think what clean core thorium energy is doing could become a real way to have that kind of US-India cooperation in reactors that can be produced in India with fuel technology and supply from the United States as an export product, particularly to developing countries that will need smaller reactors. And I'll end with that, and I'll look forward to the panel discussion. Thank you.
Thank you. Well, indeed, what you mentioned about the climate challenge, or now the right thing to call is a climate crisis, is very much here. And as I had said in my thing, you also mentioned in your presentation, without nuclear being a significant part of this solution to address the climate crisis, I in fact do not see any way. And in that also, as you correctly observed, we have to find solution on the basis of existing immediately deployable reactors, because 29 years is not too long if we have to reach the net carbon zero by 2050, which is the IPCC goal. And so I think this is both a big challenge and also, I think, a big opportunity, and we must rise to that. And so I see a lot of synergy between CCTE and Lightbridge in terms of the principal approach. The detailed approach are obviously different, but principal approach. And I do hope that this cooperation would take us much further towards our goal. Well, I think with this, now it's time for us to get into the discussion among the panelists. So this is a chance for members of the panel, if they have questions to raise to other colleagues and also to me, if anybody would like to take a lead, we can have maybe 5-10 minutes conversation in that mode, and then we can open it up to the larger audience. So would anybody want to take a lead from among the three panelists?
I can start, Dr. Kakodkar, with a question.
Wonderful.
So I for the past decade, I've had a chance to travel to India, probably about a dozen times, and have spent time with the various companies in India and organizations involved in the civil nuclear sector, and have been really impressed by the capabilities that India has in designing, in developing, constructing, and operating reactors. And I've often asked the question, why does India not have an export strategy for its nuclear industry? So many other countries that have less experience in these areas of nuclear development and construction have been exporting, but India has not done that. And I'll be interested in hearing your thoughts and how that can be turned around.
Well, I'm very happy and very glad that you asked that question. That is something which has been bothering me for not just this decade after I retired from atomic energy, but even before. I know many countries, they build their first reactor, and before they build their second reactor, they already exported 2 or 3 reactors. Now, one of the reason is, we were actually operating in a very different kind of political constraints. We had our own policy, and so arriving at the international civil nuclear cooperation itself was a major challenge. And so one could not have thought of that before, because even if we wanted to, it's not clear how the world markets would have received this. So this opportunity has really opened up after establishment of the civil nuclear cooperation. Now, then of course, we lost some time because of the liability issue, but leave that. That's not the subject matter of today's thing. And now, government, of course, as I mentioned in my presentation, has given approval for construction of reactors in a fleet mode. Now, government, as I said, there are 17 700 megawatt PHWRs under construction. Out of that, the first 6 approvals have come in pairs, 2 by 2. But the last 10 have been approved in a single shot. One paper to approve construction of 10 700 megawatt reactors to be constructed in fleet mode. So now the establishment is all gearing up to come up to that challenge. And then of course the export effort is also a significant effort. And so in this very heavy load that has come suddenly, there is this issue whether they should do now or later. But I'm sure if there is opportunity in terms of export possibility, if there is, in the sense, on part of the department or nuclear power corporation, with lesser effort, we can have higher export opportunity. I'm sure they will look at it. But that has been that kind of, to be or not to be kind of problem. You are right there, but I hope it will change.
Great.
Anyone else? Thank you. Anyone else would like to ask any question?
I'm not sure if I'd call this a question as much as I want to reemphasize something that Seth said a little bit. But the magnitude of energy requirements to get from here to climate sustainability, to get from here to lifting the quality of life around the world in some of these emerging countries that need this. The magnitude is so huge that, and not just to focus on CCTE or Lightbridge, but both of those companies should have plenty of space to fill hundreds of reactors and still not satisfy the need. And so there's a lot of need here, and including other energy sources like wind and solar and whatever. So it's a very large unmet market in a sense or emerging market is maybe a better way to say it. And I think that's not something to underemphasize or to let pass without pausing and just recognizing the awesomeness of the scale that we're trying to meet there. And another comment that I wanted to make is that the PHWR, there's a lot of discussion around the world about small modular reactors. And the PHWR is an existing small modular reactor according to many of the characteristics. I'm not deeply in that field to know if there's some reasons why you wouldn't call it an SMR, but it's on the right energy scale. The picture that you showed at the very beginning of that energy park with 4 small PHWRs together is the very definition of how an SMR would be implemented. And so there's a sense where it's there and it's ready to go. And some of these other advanced water reactors like Seth highlighted, where their fuel is targeted, those are near-term ready-to-go reactors or already existing reactors. And so the things that we're going to be able to do in the next 30 years are things that are in our hands now, whereas these advanced reactors like molten salts and advanced SMRs and things like that still have to get the first one built. And so that's, I think, a very important comment to drop right now, is that's part of this landscape we're living in.
Yeah, I think very true, very true. And I somehow feel often, first of all, nuclear itself seems to be a bad word. In fact, somebody had described as nuclear in allergy. We all suffer from nuclear allergy. And I don't see without nuclear how this gigantic problem can be solved. You can't reach net zero. I had looked at some reports. The investments required to reach net zero purely on renewable energy, which most of it is variable. In fact, as far as India is concerned, it would require investments comparable to India's GDP itself.
Mhm.
And how can we afford that? Even if one were to get capital, but people have to pay, and you can avoid maybe half or even larger part of that investment by resorting to nuclear. But it's a question of how to get over this allergy. And to me, I think these debates will always go on. What is really required is to show performance. Once people see performance, they will actually want it. Right now, what is happening is nuclear energy, in spite of the fact that it supplies a very large part, at one stage it was some 16, 17%, 18%. Now it is 10, 11%. So it has, there's a huge experience, but there is also Chernobyl, there is also Fukushima. And people don't get very much convinced about these rational arguments about safety. The trauma seems to be working much more heavily. And so it looks to me that the answer is performance. And that is where it's important. Performance in terms of deployment, performance in terms of safety, performance in terms of cost. And that is the answer to really getting the final answer to the question with which we started this meeting. So I think probably it's time now to open this whole session for questions from the audience. And may I now turn it back to Mr. Lakshminarayan to sort of moderate the audience questions.
Sure. Let me take a stab at it with Vanita. Before that, I think Seth Gray wanted to say something. He put up his hand. So would you like to go?
Oh,
Seth?
I'm sorry, Seth. I'm sorry. Please go ahead.
Well, I'll just say very briefly that the small modular reactor program in the United States began before Fukushima and before the fall in natural gas prices. And with Fukushima, it creates obviously a much greater focus on safety, but also new regulations that add to costs related to safety. And the fall in natural gas prices creates economic competition. And I think that the best way to address both of these issues is new fuels combined with those reactors that address safety and economic benefits, which is what we're doing. I'll also say that I think another change in the world is that we've gone from something of a pyramid of looking how electricity is provided on the grid, where the bottom 40% of the pyramid approximately is baseload power, like coal and nuclear, then intermediate power, like natural gas or hydro, and then maybe peaking power, like oil burning plants. And instead, now we've just had so many renewables put on the grid that provide more power than needed at certain times of day and no power at some times of day, that what we need is not the pyramid, but something that can balance with renewables with zero carbon emissions. And I think only nuclear can do that, and in large numbers, small modular reactors. And that's the future grid that will succeed or not. And hopefully we will get there to win on climate. And I'll leave it at that. Thank you.
Wonderful. Thank you.
Thank you. There's an Edumalai Ponnuswamy. If somebody can unmute his line, he had a question. He's currently working in one of the nuclear plants here in India. In the meantime, as he participates, there was a question that came up in the chat box about the molten salt reactor, the traveling wave reactor, and the existing ones. Compare, contrast is the question, is broadly what the question is. I think you've already done it, saying one is existing, the others are all new, even the first plant is there. But if there is something that you would like to add to that answer, that will be helpful.
Yeah, I can do that, but Professor Mcdovit, you want to take that question? or Mr. Seth Gray?
Could you repeat the question again? I was looking at the questions, the list of questions, and I didn't hear what was said. Sorry.
It is a kind of a compare and contrast. Molten salt reactor, traveling wave reactor, PHWR, can do.
I guess the interesting thing for me is I've worked on all of them. And there have been different times in my career where I've become associated with a reactor concept, and I thought, well, this one's crazy. And then I get involved in it, and I thought, well, this is really good. This is really good, and I really like it. I'm not talking about any of the ones you just mentioned, just so you know. But with the molten salt reactor, we ran an experiment in the 60s. We've got concepts, and there's a number of companies that are pushing them forward. But there's a long pathway before that becomes possible. It answers a few problems. It addresses some problems with respect to fuel performance and other different things like that, makes some really good solutions possible. It brings new problems to the table, such as corrosion of the vessel. And how do you operate when the fuel is always moving through the entire plant? There's different regulatory issues. The regulators don't know how to regulate a molten salt reactor yet. So it's got a long way to go. Traveling wave reactor actually is built on some solid technology, and it has some future possibilities. Again, it's another private company that they're working hard to push it forward in some variations. And everything has a context, everything has a pathway to success. And if you look at the business models for some of these reactors, they're 20, 30 years out. Molten salts, I don't know how long before we'll have a commercial molten salt reactor. If I'm pessimistic, I'd say 30, 40 years. If I'm optimistic, I'd say 20, something like that. And who says I'm right about anything? And that these things are in somebody else's hands. And so I'm just an observer and a participant. In my lab, we were making live molten salt for a particular concept that might be built in the next 5 years. We've worked with nitrides and metals. I've worked with the traveling wave reactor and the fuel performance and the fuel fabrication of that. So all of these are on a path that gets them to a goal later. But as I've noticed over the last 30 years, you make a 25-year plan, and you have to change it every year because of what happened in the next year. So there's a lot of ground to cover before some of these become close to being realized in construction, as opposed to taking something that's already has a reactor with a fuel slot, and you qualify the fuel to fit into that reactor. That's a much more near-term solution, I think.
Great, thank you.
Doesn't mean I won't work on these things. I find them all fascinating, and I like them all.
Vanita, is Elumalai Ponnuswamy's line open?
Let me just check quickly.
He's given in the chat box. He's an electrical engineer, an energy auditor from Chennai, presently at Pickering, Canada, where an atomic station is decommissioned. So he's requested saying, please permit me to ask a few questions. As this line is opened, I just want to read out the next question. Maybe Seth can take this. If nuclear submarines are kosher, can we use that model to set up 1,000 locations, 220 megawatts? Can we use global delivery model with an on-site in India, offshore in global grid, etc., etc.? Any ideas on, these nuclear submarines, aircraft carriers that are powered by nuclear plants? Can they be used?
Well, clearly the navies that have reactors powering ships, aircraft carriers and submarines, have small reactors. These do not have very large reactors powering the ship. So the world has many decades of experience of powering many hundreds of ships with small reactors that operate very safely. And many of those designs on the ships are similar in some ways to the reactors on the land, smaller versions. Some are pressurized water reactors, some are boiling water reactors, some are other designs. And many of these small modular reactors that are coming are similar. So NuScale is a pressurized water reactor. GE Hitachi's BWRX 300 is a boiling water reactor. Now they're not the same as on submarines, but similar technology. And so I think we know that small modular reactors can be produced, they can be operated safely, Now the question is, can they be made in ways that can be built and operated cheaply? If you look at aircraft carriers and submarines, those reactors are very expensive. So technologically, yes, but now there's innovation involved on fuel and on how we build the reactors, including at shipyards, factories, shipped to the site, and ways to hold down costs. And I'm optimistic on that from what I've seen.
Okay. Thank you. And this Elumalai coming on, he has been Vanita? No, it looks like...
I would like to add one, Mr. Narayanan, with your permission. Earlier, somebody asked a question about the molten salt reactor in compared to heavy water reactor.
Yeah.
And I think heavy water uses the solid state fuel, whereas molten salt uses fuel in a molten state to begin with, which doesn't exist today. And secondly, there is a reprocessing that is involved in molten salt reactor at some stage. And that's where the concern rises with the, if you were to use thorium, the reprocessing for thorium has not been established in the industry yet. Whereas using fuel like anil fuel in pressurized heavy water reactor, we have eliminated reprocessing completely out of it. So that's why it makes it heavy water reactors much more desirable to deploy in short term. I just wanted to add that.
That's good.
Yeah, I think Erumalai Konaswamy is online. He can probably...
Yeah.
Hello.
Please go ahead, Elumalai.
Yeah. Good morning to all of you. I am from Canada, Pickering. Just 3 to 5 kilometers away from the decommissioned Pickering Atomic Power Station. So as an engineer and energy auditor, I am aware that nuclear energy has got unparalleled advantage with respect to the fossil fuel generation. My question is in 2 parts. One is safety is discussed in length. Second is the project cost and the operational cost, life cycle cost is conspicuously underplayed. Now, what is the hesitation on the part of the insurance companies to have insurance with the atomic power station victims if some eventuality happens? That is one part of it. Secondly, this America, which consumes more than 20% of the global energy consumption, which has the natural resources, finance, technology, and everything, is not improving on their energy mix on atomic energy. And thirdly, with respect to India, see, we have got a very bitter experience of handling the victims of Bhopal gas tragedy. Our government is more concerned about the corporates of multinational companies and not for the people. That was the past experience. So it has got 2 components. One is the safety. Second is our preparedness and the empathy of the governments to meet any eventuality to compensate the victims.
Thank you.
Already in Canada, 82% of the energy mix is non-fossil fuel. That is carbon zero. Only 18% is with fossil fuel. So why can't we think of reducing the consumption, the demand, and to the extent that we can acquire the renewable energy? Thank you. And then also doing some low-hanging fruits like converting the transport to electrical vehicles. Then opting for it.
Yeah.
Thank you. I think
you.
we have other participants waiting as well. Yeah.
Yeah. Go ahead.
Yeah.
Kutman.
I'll do that, but Ms. Teplinsky, would you like to address the insurance part to begin with? And then I'll come back on this.
Sure, but I was having a little bit of trouble with sound in making out the question. What is the question about insurance?
See, if you say it is so safe, why should not the insurance companies come forward to insure to make any compensation for the victims in case of any eventuality?
Yeah. Okay, I understand. Thanks for repeating the question. So there is a global nuclear liability insurance scheme that was designed. It's been in play for the past 40, 50 years. And the idea behind the way that the insurance scheme is designed is that it makes most sense instead of having to insure every single party in the supply chain and in the operation of the nuclear power plant to insure only one party, and that is the party that owns and operates the plant. So, insurance companies, as many people on this webinar know, nuclear is very specific. It's very technical. Insurance companies do not want to simply insure nuclear without understanding all of the issues involved. So for that reason, there have been specific nuclear insurance schemes created to support nuclear operation. And there is worldwide insurance available that supports nuclear operators and is issued to nuclear operators. And in the case of a nuclear incident, in most regimes outside of the United States, liability is channeled to the operator, which means that the operator's insurance then comes into play, and the operator's insurance covers all liability, all victims, all third parties. In the United States, we don't have the legal channeling. It's actually by insurance. So anyone can be liable, but the insurance covers anyone's liability under the process. So there is billions of dollars of insurance available in the world. Each country has its own nuclear insurance pool. So the insurers do, in fact, insure nuclear. It's just that they do it in a most efficient way.
Well, on this aspect of why can't we live a why can't we reduce our consumption? Why do we want so much of energy? Now, this is true that correlation between energy consumption and quality of life or human development index, there is a correlation and there is a big scatter. So there are obviously many other factors which are at work. But the fact is, I read somewhere a very nice description, and that is, while in principle, reducing consumption and living an austere life is a right philosophy, some people will pursue for some time. It's doubtful whether some people will pursue for all time and whether all people will pursue for even some time. This is a civilizational issue. And I think it is, in the sense, if there is something happening in some part of the world, and if everybody knows that there is energy at the kind of root of addressing this better quality of life, obviously other countries would want. You can of course change the pattern, the elasticity, and maybe earlier we require much more energy for a given HDI. Maybe today the devices have become efficient, the intensity, energy intensity has come down. So all that is important, but I think the need for energy cannot be wished away in my view. Now, there is, example of Kerala was given, and this is very nice that this is happening. But at the same time, we have to think about an interdependent nation or interdependent society, and whether you import energy, whether you produce energy, whether you import energy, or whether you import goods, effect is the same. It's somewhere else the energy gets consumed. So on the whole, if you take the average, I think you cannot escape that conclusion. And I have followed Gandhian philosophy in some detail. I have been close, my family has been close to Gandhian way of life. But I have come to the conclusion that I'm not a champion of living in an extravagant way at all, nothing of that sort. But I think there is something civilizational, that dimension we cannot ignore. Thank you.
Sir, how do you compare the 40% increase in per capita consumption of the United States with respect to Europe?
Well, I told you that there is that scatter, and we are
Which
not
one
talking
will have a
about
benchmark?
You know, for example, no, I'm coming to that. For example, for India to reach HDI comparable to United States, we have to increase our energy consumption by a factor of 5 or 6 to reach that HDI. To match US, probably we have to increase by a factor much bigger than that. Now, surely there is a 40% scatter, 60% scatter in this. But I think we should not lose the big picture for want of these comparisons. That's the way I look at it.
Thank you, Kakodkar. I think we have approached the closing time. I just want to see if
you missed.
each one of you would like to make a 30-second final comment, please, and then we can close the session. Thank you. Maybe we can start with Elena and conclude with Kakodkar.
Sure. Happy to start. So I think it's, everything has been summarized quite well here. There is, a huge opportunity for nuclear energy to be a key driver of deep decarbonization, which is urgently needed because of the climate crisis that we're in, and the increase of that climate crisis that we're facing. There needs to be a way to address the large-scale deployment of reactors using existing technology fueled with new types of fuel is one key way to address this. The other issue is bringing down the costs. And certainly the idea that India, which has 40 years of experience with small reactors, could export reactors to developing nations at low cost, seems to be, to me, is a very interesting option, and I think needs to be explored further.
Thank you. Seth or Dr. Mcdovit?
I'll start. Thank you. The question we are addressing today is nuclear energy a solution for sustainable development? And I think the answer we've arrived at is yes, that substantial growth in nuclear energy is a necessary component of the growth in energy in the world and replacing current non-sustainable energy. And without substantial growth in nuclear power, the world will not meet its climate goals. And as Alina said, I think this has to be with existing reactor technology with new fuels. And I think that if we're going to have such an expansion of nuclear power so quickly, that is the only way to do it realistically.
So I won't make real long comments, but I would just share the thought that with all the different big picture complexities that have been brought up, from population to quality of life to climate change, those are all really large. And this discussion we're having, the sustainability of nuclear, is a part of that answer to the challenges of the world. And as I alluded to earlier, the reason I got excited about the field that I work in and continue to work in is my optimism to work on something that actually makes an impact around the world and makes a difference. And this is a direction where a new nuclear fuel concept is not just a cool toy in my laboratory, but it is something that has a reach to change society. I mean, I don't want to sound too pie in the sky there, but it really has that potential to be that level of impact to the world. And so that's something I'm very optimistic about.
Thank you. Kakotkarji.
Well, first of all, I think we had an excellent conversation. And I really feel, as I said in the beginning, that I think we are approaching the crisis point, and the climate crisis, in fact, its impact on the world is going to be far, far higher than what we have seen in the COVID-19 pandemic. Now, and we obviously cannot wait and see that happening, because all this preparation takes time, and this 30 years is really not too long in that context. And so I think we need to sort of get our act together. And in India, anything high tech, because the cost of living is much lower compared to advanced countries. At the same time, we have very competent youth, young human resource. We end up doing high-tech work at a much lower cost, typically half. And that's behind why these PHWRs are cheaper. Well, if we make PWRs tomorrow, that also you'll find the same answers. So, in fact, I have been telling my colleagues from Westinghouse and EDF that you manufacture your PWRs 100% in India, and you'll finally become competitive, which is not the case. That's exactly the point. And to me, this is a great opportunity between India and United States to take reactors from India, take fuel from United States, and address the energy problem of the new world, where there is, there is an issue of decarbonization, but there is also an issue of new energy supply, and all by clean energy source. And base load nuclear energy has to be necessarily a significant part of that. So I think it's a win-win opportunity. Only thing is, we must all work together to address this. Otherwise, the destiny will not forgive us. Thank you.
Thank you very much. Thank you very much, all the panelists. It was a very interesting conversation. Lots of insights, clear direction. This is not a debate. It is a unified voice talking about the future. Thank you. On behalf of CIC, I extend my gratitude to all of you for participating in this very interesting session. Thank you.
Thank you. And thanks all panelists once again. Thank you.
Thank you, Dr. Kakodkar, Mehucha, and all the panelists and the audience who turned up today. Coming up next on 23rd of April is Principal Economic Advisor Sanjeev Sanyal is going to be here in Chennai. Hopefully, we can still pull it off, and the COVID cases are spiking, but we hope we can, somehow pull it off. Let's see. He's going to speak about policy making for an unconventional world. So we will have the mailers sent to you all, and look forward to another exciting event. Thank you very much.